Welcome to section 2.4 of the chain rule. In this section, we're going to talk about how to take the derivative of composite functions. So let's first talk about the differences in the left side of this column and the right side of the column. On the right side of the column, notice that on this first function, y equals the square root of x squared plus 1, we have both a square root function and a quadratic function. And the quadratic function is on the inside of the square root function. This makes it a composite function, and we'll have to use the chain rule in order to take the derivative of the square root of x squared plus 1. On this second one, y equals sine of 6x, if we put in some parentheses around this 6x, it makes it a little more obvious that the 6x is a linear function, and then the sine of 6x makes a composite function. On this third one, we have a linear function inside of a fifth degree polynomial. And on this last one, we have a quadratic function inside of a trig function. On the left column here, you'll notice that we don't have any inner and outer functions as we do with the right side column. So in order to take the derivative using the chain rule, right, what we'll do is take the derivative of the outer function, leave the inner function the same, and then multiply by the derivative of the inner function. Right? So derivative of the outer function leaving the inner function times the derivative of the inner. All right, and a lot of times I'll refer to this inner function as blah. So the derivative of the outer, leaving the inner the same, times the derivative of the inner, will be the derivative of the outer with blah times d blah. So let's see how this works in some example problems. All right, on this particular function, example 1a, we have a linear function that's in the bottom of a rational function. So we have a composite function here. So our inner function, u equals x plus 1, right? And y equals f of u is y equals 1 over u. So you see, if I take this x plus 1 and plug it in for u, I will get back my original composite function. Same thing with this example 1 part B. If I put parentheses around this 2x, it's a little easier to see that u equals 2x. All right, and my outer function would be y equals f of u, so it's the sine of u. If I take this 2x and plug it in for u, I will end up back with my original sine of 2x. On 1c, our inner functions, u equals 3x squared minus x plus 1, and then my outer function is the square root function, so the square root of u. All right, last one, example 1d. We want to rewrite this y equals tangent squared x as y equals the tangent of x quantity squared. All right, so we have a trigonometric function with the tangent x, and then we have a quadratic function, this second degree here. So u is our inner function, the tangent of x, and our outer function is u squared. All right, so let's look at example 2. And before I do example 2, let's talk about the general power rule for the chain rule. All right, and this will go back to the derivative of the outer leaving the inner the same times the derivative of the inner. If you notice here, if we have an inner function raised to a power, that just like our original power rule, we multiply the n down to the front and decrease a power. The only additional step that we have is now we have to multiply by the derivative of whatever was inside. All right, so let's look for the derivative of y equals x squared plus 1 cubed. So what we're going to do is take the derivative of blah to the third power. All right, so this x squared plus 1 is blah. So the derivative of blah to the third is going to be 3 blah to the second. And then one more step is to multiply by the derivative of what we see on the inside here. All right, if we clean this up and actually take the derivative of that inner function, we have 3 times x squared plus 1 squared times the derivative of x squared plus 1 is 2x. So it's just the power rule with one additional step, multiplying by the derivative of what's inside of that power. Let's look at another example. All right. So we're going to take the power rule, multiply the 3 down to the front, and decrease it to the second, leaving the inside the same. One more step, multiply by the derivative of the inside, which is 3 minus 4x. And that's done. On example 3b, we need to rewrite this first as x squared plus 1 to the 2/3 power. Remember, the index on the outside is always the bottom of the rational exponent. Now that we have something that looks like the power rule, we apply the power rule. So y prime equals 2/3 times x squared minus 1 to the negative 1/3. I multiplied down to the front, this 2/3, and then decreased 2/3 by 1 power and made it negative 1/3. One additional step, since I had an inner function, which is quadratic, I got to multiply by the derivative of that quadratic. All right, let's first rewrite this as negative 7 times 2x minus 3 to the negative 2. Now let's apply the chain rule, and for this particular problem, it's a modified power rule. So y prime equals multiply down, so negative 2 times negative 7 gives us 14. Leave the inside the same and decrease a power. All right, so that is the power rule, multiply down, decrease power. But since the inner function is something other than x, we have to multiply by the derivative of the inner function. So the derivative of 2x minus 3. So the final answer is going to be y prime equals 14 times 2x minus 3 to the negative 3 times the derivative of 2x minus 3, which is 2. We could rewrite this if we wanted as 28 over 2x minus 3 to the third power.